Hey math people, lecture 2 of chapter 1 of Calculus 1. So we're going to start the day off looking at some connections between asymptotes and limits. Those seem to have some connection. What is it? You'll find out. We'll evaluate some limits using that logic. We'll look at limits with what we call relative growth rate. We'll look at some weird ones, cover what's called Sandwich Theorem, which is a blast, and then just go through general limit properties because we have to throw that in somewhere. So just remember to use the timestamps. This lesson was custom made for you, Sarah. Made up that name. It's meant to be a tool for anyone, so just click around if you need to. Remember, you can do this. Just be patient with yourself and pause when you need to. Okay, so starting from the top, do you remember asymptotes? Yeah, that was a thing from like Algebra 2 or something. We have horizontal asymptotes. Horizontal asymptotes go this way, like the horizon, and then vertical asymptotes go up and down, vertical the other way. Here we're just worried about horizontal asymptotes, so feel free to pause if you'd like to. I'm going ahead with this. Remember the rules behind this. If your denominator's power is larger than your numerator's power. So in terms of the algebraic expression, the variable. So here we have a power of 1, and then here we have a power of 0. It's x to the 0th power here. We have a horizontal asymptote at y is equal to 0. I can show this. I'm going to go ahead and graph it. 1 over, and then this is 2x plus 3. So this asymptote here, long run behavior, horizontal left, right, and we see that at 0. Okay, what if you have a power match? So for example, you have a 1 as the power of this x and a 1 as a power of this x. You take the leading coefficients, and the idea behind that is if you plug really big into top and really big into bottom, plus 4 and plus 6 do nothing in the face of infinity, and you just have like 3 times infinity and 5 times infinity, so that ratio maintains the same. So we're looking at 3x plus 4 all over 5x plus 6, and you get this asymptote at y is equal to 3/5. No, fifths. You can see here it gets real close on the right side, and it gets real close on the left. All right, the last one is if you have a higher power up top, numerator blows up, there's no horizontal asymptotes. You maybe get like slant asymptotes, oblique asymptotes, that stuff. I don't care about that. Not for this. Okay, next up is connecting the asymptotes with limits. So is there a connection? Yeah. A horizontal asymptote is the same thing as if we take the limit to infinity and get a finite number. Consider how that kind of just makes sense, right? If I run this black curve to infinity, right? So I go forever in this direction. We're getting infinitely close to 3/5. We're getting real close to that 3/5 value. There it is. Right, 3/5 is 0.6. These values are getting closer and closer to 0.6. 0.604, 8, 0.6047. You got to just keep going. We're only at 16.4. You got to go all the way. You got to go big to see that one. It's approaching 3/5. For vertical asymptotes, that's the one that goes up, down. It's just flip-flopped, which is kind of cool. So instead of approaching infinity and reaching a finite value, you're approaching a finite value and you're getting infinity as a solution. So you just take the infinity and finite value, flip it, and then you get a vertical asymptote. You flip a horizontal line to a vertical line. All right, so find the asymptotes and then write the accompanying limit statement. We're just kind of making that explicit connection. Feel free to pause if you want to, but I'm going to show you the answers in 3, 2, 1. So for the first one, we have a horizontal asymptote at 2. And the reason why is we have x squared down below and then like a 2x squared up top if you FOIL them out, multiply them out. So it's the same powers and you get a horizontal asymptote at 2. The vertical asymptote occurs when you think about what the bad guy number is down in the denominator. If I attempt to plug in 3 down below, you get 3 minus 3 is 0. Which is bad because then you get a number over 0, and that's how you create your vertical asymptote. So we would then, approach these scenarios like, do we ever hit 2? The answer is no, but we approach 2. Do we ever hit, or can we plug in 3 rather? No, but you can approach 3. So if we were to look at this graphically and just make those connections, because that's what math is really all about, by the way. If you think math is just, all right, just tell me the answer, you're doing it wrong, sort of. No flame. But math is about the conceptual connections. creating like a basis of understanding, yada, yada, yada. You don't want to listen to that, and I don't either. So if we look at that horizontal asymptote, we can see here it's at y is equal to 2. So long run behavior to the left, long run behavior to the right. We're just running towards the right here, infinity, but it's the same in both directions. So that would be that limit statement. Try to absorb that, right? And then we have that asymptote of x is equal to 3 for when it's vertical. You can see it kind of volcanoes up a little bit here. And really think about this statement and how that associates itself to the purple line. And I like to dash them sometimes, like, okay, these are asymptotes, these aren't on the graph. So this is associated with the green line, so pause and think. And this is associated with the purple line. So really pause and think about that. All right. Okay, so looking at the rest, you can't plug in 0, so that's your vertical asymptote. And then the horizontal asymptote, it's just shifted 4 units up. Gotcha. If you were thinking, oh, shouldn't it have just been 0? Well, I just added a 4 at the end, so I was trying to be a little sneaky. And you get these associated limit statements. The natural log is a graph that we hope you know, and it has a vertical asymptote at 0, so we went ahead and wrote that there. It has no horizontal asymptotes. And e to the x is the inverse of log, and it has a horizontal asymptote. So when you're dealing with inverse functions, the vertical asymptote turns into the horizontal asymptote. All right, done. We can also just now evaluate like general limits too. We don't have to connect them to the asymptote unless we want to. Sometimes that can conceptually help. So try these out, 3, 2, 1, bam. All right, so if we're looking at the first one, you kind of get a little like, what's going on there with that square root? The square root of x squared is literally the absolute value of x. This is a niche knowledge moment where this could occasionally be helpful. In this case, it is. So this is sort of to be treated as like the absolute value of 2x, because that's the square root of each of these. The plus 2 and the minus 2 do not nothing, but close to nothing in the face of infinity, right? We're plugging in big number. Infinity plus 2, infinity minus 2, who cares? That is essentially nothing. No difference. So we get the absolute value, and I like to speak this way sometimes with limits, the absolute value of 2 big over big. Well, these bigs kind of just cancel, and you just get 2. That's the long run behavior. Look at the graph if that's like, whoa, a lot for you. But it's the same concept of matching powers, so therefore just circle leading coefficients. It's that ratio of, so similar to the warm up here, it's that ratio of those leading coefficients. I just had some fun with the absolute values. If we're going towards negative infinity, well, we had an absolute value in play with that square root of square. I'm being tricky here on purpose if this feels like a lot. If you feel like this is light work, then good for you. So we have a positive up top and a negative down below, so it's a negative 2, whereas before we had a positive over a positive. Arctan is a graph that you should know for the course. So tangent looks like this. Arctan actually doesn't look like that. I'll show you guys arctan. Arctan has 2 asymptotes. It has, what? Where'd you go? Huh? Oh, here we go. Ha. Arctan has 2 asymptotes. It has, and they're both horizontal asymptotes. It has one at pi over 2. So the reason why it's there, think about why we can't plug in pi over 2 or negative pi over 2 into tangent. You get 0 in the denominator for sine over cosine. So you have these, just have one loop of around the unit circle with this expression. So there are certain graphs in this course. So you have 2 horizontal asymptotes, pi over 2 and negative pi over 2. There are certain moments of the course where we ask you to like remember stuff from like pre-calc. So perhaps your teacher would put this on a test, maybe they wouldn't. But you just have an asymptote. You have a horizontal asymptote at pi over 2. So therefore the limit as you approach infinity is pi over 2. The last one here, I think I put this here because this is like the half-life of like caffeine. So like if you drink 100 milligrams of caffeine and you let time go on till the end of the universe, you won't have any caffeine left in your system. That should make sense. But it kind of slowly tapers off. So you do have a horizontal asymptote at 0 for when you have like exponential functions. Think about like exponential growth, exponential decay. You generally have an asymptote there. Okay, some of those are really tricky, but if I were to summarize it, still think about, for the top 2, think about just general same power, power higher in denominator, power higher in numerator kind of logic. And for C and D, sometimes knowing the graph is beneficial. I would say some teachers would be inclined to give the graph for C and D. All right, so now what about like relative growth rate? So we already kind of started this conversation. If we go back to the warm-up, we see that these kind of grow together. 3x is a line, 5x is a line. They grow similarly. Whereas if you look at C, this is a parabola up top, and this is a line down below. The parabola outpaces the line toward infinity, so there is no asymptote. So there wouldn't be a limit for that one. The limit towards infinity would just not exist. So looking at the kind of like growth rate comparisons between certain function types, I'm going to show all of these in a moment, but think about it logically first. If you just look at only A with me, if we run towards infinity, what probably grows faster, the exponential or the parabola? You know, if you think it's the parabola, then that means that you believe that denominator would outpace numerator and you would go towards 0 over time. But if you think it's the exponential, you think that the numerator blows up and the denominator stays small over time. So then you would think that it would be does not exist or infinity, right? So that's really the answers for each of these. So I just want you to quickly scan them. I want you to think infinity or 0 for each of these, if you'd like. 3, 2, 1. So here's the speed hierarchy. The exponential, there's a reason why we like say, oh man, this is growing exponentially. And that's like a big deal because exponential growth is very fast. So that outgrows parabolic growth by quite a bit. Imagine if gravity behaved exponentially. That would be crazy. So gravity is like quadratic. So it's power 2. It's a little more reasonable. So anyway, you get super big over big. That's infinity. If we look at sine just goes up and down and up and down and up and down. I like to think about it, if this was like a race, the exponential would take first, the polynomial would take second, the radical would take third. Log finishes the race, they get a 4th place finish, but does not finish as your trig functions. They just go up, down, sine and cosine. They just go up, down, up, down, up, down. So you have small over big, that's 0. The log is slower than the cube, so that's also 0. And then over here, this one's a little tough, but technically the power is higher up top. Up top. Because if you rewrite this as a rational exponent, you get x to the 3/2 up top, and you get x to the 2/2 down below. You have a higher, faster numerator. So even though this plus million is helping, technically, the x to the 2/3. It's nothing in the face of infinity, so the numerator is faster and the numerator wins out. If numerator wins out, it's infinity. If denominator wins out, it's 0. Okay, there are some weird limits, and this is kind of for fun to like cover my bases, but if you were to graph each of these, they look wild, all right? We actually get our 4th type of discontinuity, known as the oscillating discontinuity with B, and that one's just like a fun one to look at. We saw sine x over x for approaching 0 in the last lecture. It's just one that some teachers like to have you memorize. For this one right here, really think about what happens. You never can quite get 0 inside of sine, and sine of 0 is 0. So it actually just gets forever close to 0, but never actually hits it. So it goes up and down and up and down and up and down faster and faster and faster and faster when it gets closer and closer and closer to 0, to a point where like immediately to the left or right of this, it's just infinitely drawn up and down like some mad angry math teacher just staring at students that don't do algebra correctly in a calculus class, just wasting all the ink on a board or something. It's ridiculous. It's called an oscillating discontinuity, and there's a very good chance that you don't need to know it for your class. This is also just another fun one, but the bottom line is sometimes you have these limits where like algebraic techniques may not work, and you have to just look at the graph. Or there's another philosophy to it, but that's like later in the course. Okay, another like fun theorem is called the Sandwich Theorem, and it is best taught through this meme. I'm actually confident of that. So we can look at this math in a second here. The idea, and I'm going to show this graphically, is that if you can squeeze or pinch or sandwich an unknown weird boy limit, something like this, in between 2 known limits, then you're forced into being able to call whatever that middle forced meat of the sandwich is to be the same as the two buns. So I'll show you what I mean, all right? You're kind of thinking, what the heck is he talking about? We'll look at the math in a second. because conceptually this can be like kind of not easy. If I were to graph x squared cosine of 1 over, I gotta get better at typing these. This is what the graph looks like. All right, some weird stuff happens when you get close to 0. It kind of creates this like, what's going on? I mean, clearly it looks like we're approaching 0, but we can prove that it's equal to 0 by sandwiching or squeezing or pinching this kind of fun curve of a graph. So like if I were to graph x squared and I said, what's the limit as we approach 0 of x squared? It's 0. You do a direct substitution, nothing crazy. And you do the same thing for negative x squared. You can see that we're pinching, we're sandwiching the weird function. So I don't know, I'll make these buns. Orange or bun. There. And then the meat. It's some funky blue moldy food. There we go. We're pinching it such that the limit as we approach 0 for this expression must also be 0. So if we look at this, if you have two outer functions that are always fencing the middle one, which you can see that's what's happening here. It's kind of a fun design. And you can say that the limit of the two buns is 0. Then the limit of the middle, the meat, is also 0. That's all it's trying to say. Depicted by Gordon Ramsay. So we also have just a few rounds of examples. The primary idea behind these is that you're trying to squeeze the sine or cosine between two values, and to spoil some of the fun or teach it, really think about what is the highest that sine can be and what is the lowest that sine can be, right? And it's the same story for cosine. Really think about that. I'm being quiet for a reason here. What's the highest that sine can be? What's the lowest that sine can be? 3, 2, 1. 1 is the highest that these functions can be, right? 1, 1, 1, 1. And then the lowest these functions can be are -1. So in terms of the actual practice of what you probably have to do as the, Calc AB student or Calculus 1 student, you just gotta replace sine with 1 and replace sine with -1. So I'm going to show that right now. If you replace this sine of 1 over x with just -1 and 1, you just get x squared and -x squared. And we know those limits. You just plug in 0. So then the solution is 0 for the middle function, the meat. Likewise, the same story occurs for both of these other ones. So I replace sine with 1 and -1. I sandwich the functions. I create the limit of the buns, and then I produce, therefore the limit of the meat is the same. We're seeing lots of zeros here. So like if we wanted to say bottom line, can you guess 0? Maybe, but I don't know. It depends. Personally, I put like one question of these on like my first midterm, and then I don't show it ever again. But it is a useful idea. There are moments in math, like upper maths, where I'm like I don't know, I'm working through a proof or something like that. I'm like, oh shoot, I need sandwich theorem here. So if anything, if you're just kind of cool with the concept, then I think you're in good shape. That's me though. Lastly, limit properties. If the limit exists, you can just do math as you would expect, which is so informal, but trust me, it is not worth, like if you're just a Calculus 1 student, you're in business calc, you're just trying to get through this last math class or whatever, you don't need to know all the fancy formalized definitions. The bottom line is you can just pluck out a limit or toss it in if you have like addition, subtraction, multiplication or division occurring within your algebraic expressions on the inside. I'll show you what this is in a second, but the only last little thing I'll say to this that does matter is the limit has to exist and you can't divide by 0. All right, so if that last 20 seconds you're like, what is he talking about? Let me show you. So we have, we're approaching some value a for some abstract function, f, g, and h. If you know that the limit as you approach this a, let's just say it's like 2, is 1. And then if we approach it for a different function, that limit is 2. And then if we approach this value for a different function, that value is 3. You can distribute, quote unquote. I'm being very hand wavy here, but the idea is to lean into the intuition behind this. You can just say, well, okay, you follow your intuition here. If you can kind of like distribute the limit, which, hand wavy, isn't this just 1 plus 2? Yeah, that's what it is. So if you want to just test your knowledge on the rest of these, feel free. I'm going to show the answers in 3, 2, 1. Limits behave as expected. So why is this covered? You should cover like a proper math course will cover properties of whatever the new move is. But more importantly, when you get into derivatives and integrals, this is not true. Like you can't just make these assumptions like this. So big warning right now. We're in the nice, lovely land of limits. Look at that alliteration for you. And limits are not too bad. When we get into derivatives soon, next chapter, we're going to need what's called the product rule or the quotient rule to handle some of these other cases. Anyway, that's it for you. Math on.